November 15th, 1886, Cleveland, Ohio. The machining report from visiting British manufacturing specialists would never fully capture what they witnessed that afternoon. American factory workers, changing cutting tools on turret lathes using methods that defied everything European precision manufacturing said was necessary for quality production. Through the steam and grinding steel of the Carnegie Avenue factory floor, identical bicycle hubs moved through six-station turrets with timing that seemed impossible to European observers. No master craftsman measuring each setup, no hour-long tool positioning rituals, no individual adjustments per operation. Yet they produced parts with consistency that European hand-set lathes could not match. In European workshops, skilled machinists required 60 to 110 minutes to change a single cutting tool. Each setup was essentially custom, different measurements, different positioning methods, different precision outcomes. Most required years of apprenticeship to master. The Americans were operating with manufacturing philosophy the Europeans had never imagined possible. Preset tooling, mechanical stops, 45-second changeovers, production rates that transformed semi-skilled workers into precision manufacturers. 800 miles from European machine shops, the most decisive tooling revolution in industrial history was revealing itself, not in superior craftsmanship, but in the mechanical systems that eliminated setup time entirely. Worcester Warner stepped off the Pennsylvania Railroad car at Cleveland's Union Depot on March 23, 1881, carrying blueprints for precision machine tools and ambitions that stretched far beyond the sooty industrial landscape spreading before him. Beside him, Ambrose Swasey hefted their shared toolbox, its weight representing everything they had salvaged from their partnership at Pratt & Whitney in Hartford. The two men had pooled their savings, $3,000 between them, to establish Warner and Swasey Machine Company in a city that promised skilled mechanics, abundant iron ore, and proximity to the expanding railroad networks that connected America's growing industrial centers. Within weeks, they had secured a modest brick building on Carnegie Avenue near East 55th Street, its windows facing the sprawling Case Western Reserve University campus. Cleveland's bustling economy, fueled by steel mills, shipbuilding, and emerging bicycle manufacturers, seemed to offer unlimited opportunity for precision machining services. Yet as March turned to April, Warner and Swasey encountered the same problem plaguing every manufacturer from Boston to Chicago. Tool changeover time consumed more hours than actual production. The mathematics were brutally simple. Traditional engine lathes required complete reconfiguration for each new operation, and the process demanded both skill and patience that most state-owned American shops could not afford. Heinrich Zimmermann, master machinist at Cleveland's Germania Machine Works, demonstrated the European standard during Warner's first week in the city. Removing the current cutting tool from the lathe's tool post required careful attention to avoid damaging the delicate cutting edge, 5 to 10 minutes of methodical loosening and lifting. Installing the new tool holder demanded precise alignment with the lathe spindle axis, another 10 to 15 minutes of adjustment and tightening. Measuring and positioning the new tool exactly where the cutting edge would engage the workpiece consumed 15 to 25 minutes of careful calculation, measurement, and incremental movement. Then came the critical test cuts and adjustments. Zimmermann would engage the tool with a piece of scrap material, measuring the resulting cut with micrometers accurate to thousandths of an inch. The first attempt rarely achieved the desired dimension, requiring another 20 to 40 minutes of repositioning, testing, and remeasuring. Final measurements and fine-tuning consumed an additional 10 to 20 minutes as the master machinist brought every variable into perfect alignment. The total setup time ranged from 60 to 110 minutes per tool change, and complex parts requiring multiple operations. Turning, drilling, threading, boring meant hours of setup between each step. A simple bicycle hub required 6 different operations, transforming what should have been 30 minutes of actual cutting time into a full day's work when setup time was included. Warner calculated that European-trained machinists like Zimmermann spent more time setting up their machines than operating them. European manufacturers, particularly British firms like Herbert and Ward, dominated precision manufacturing because they could afford armies of highly skilled tool setters. Their apprenticeship systems, refined over centuries, produce master craftsmen capable of achieving thousandths of an inch precision through hand-eye coordination and tactile sensitivity. German workshops employed specialists who devoted entire careers to perfecting single aspects of tool positioning, their knowledge passed down through generations of guided practice. American manufacturers faced an impossible choice: hire expensive European-trained machinists at wages that made their products uncompetitive, or accept inferior productivity that relegated them to crude, low-precision work. Jonathan Hartwell, who operated Cincinnati's largest machine shop, had built his reputation by recruiting German immigrants and paying premium wages for traditional European methods. Yet even Hartwell admitted privately that his costs were unsustainable against British competition. Warner and Swasey, experienced from their years developing precision measuring instruments at Pratt & Whitney, recognized a third option that industry experts considered impossible: eliminate setup time, entirely through mechanical innovation. They had witnessed Stephen Fitch's 1845 turret lathe concept for producing interchangeable percussion locks at the Springfield Armory. The idea was mechanically sound: a rotating turret holding multiple cutting tools that could be positioned and locked without individual setup, but execution remained crude and unreliable. Industry experts dismissed preset tooling as a fundamental impossibility. Tools required individual adjustment for each job. That was simply the nature of precision work. No mechanical system could replace the craftsman's eye and experience in achieving the minute adjustments that separated acceptable parts from precision components. The American Machinist Journal published editorials arguing that mechanical positioning systems would never match human judgment in accommodating material variations, tool wear, and thermal expansion. As orders poured in from Cleveland's growing bicycle and sewing machine industries throughout that first summer, Warner and Swasey realized the opportunity was larger than anyone had imagined. Columbia Bicycle Company's production manager, Samuel Winton, desperately needed 500 identical hubs per week, but could only secure traditional machining capacity for 50. The bicycle boom was creating demand for precision parts in quantities that traditional methods simply could not satisfy. Their first attempts at mechanical tool positioning failed miserably. Tools wandered during cuts as vibration loosened their improvised mounting systems. Positioning was inconsistent, with variations measured in hundredths rather than thousandths of an inch. Parts that should have been identical varied enough to require hand fitting during assembly. European competitors, monitoring American innovation attempts from their London and Munich headquarters, sneered that American shortcuts would never match traditional craftsmanship. By 1885, Warner and Swasey faced mounting financial pressure and industry skepticism. Their original $3,000 investment had grown to substantial debt as they pursued mechanical solutions that consistently fell short of production requirements. The dream of instant tool changes seemed as distant as European manufacturing supremacy seemed permanent. Yet Warner continued sketching mechanical arrangements in his notebook, and Swasey spent evenings in their workshop machining experimental tool holders with precision that exceeded anything their competitors could achieve by hand. The breakthrough emerged from an unexpected source in the spring of 1886, when Warner and Swasey received their most prestigious commission yet, constructing the largest telescope in America for California's Lick Observatory. The project demanded precision that exceeded anything they had previously attempted: optical components requiring accuracy measured in fractions of thousandths of an inch, mounted in mechanical systems that could track celestial objects across the night sky with clockwork precision. Swasey spent weeks designing the telescope's mounting system, sketching gear trains, and bearing arrangements that would rotate smoothly under loads exceeding 2 tons. The mechanical challenges were staggering. The telescope's primary mirror, 36 inches in diameter, required a mounting cell machined to tolerances that traditional hand fitting could never achieve. Every component, from the declination axis to the hour angle drive, demanded multiple cutting operations performed with absolute consistency across dozens of identical parts. Traditional machining methods would have required months of individual tool setup for each telescope component, with master machinists spending more time positioning tools than cutting metal. Swasey realized that the astronomical precision required for the Lick telescope demanded the same systematic approach they had been struggling to develop for mass production. pre-positioned tools that eliminated human variables from the manufacturing equation. The revelation struck him while examining the telescope's focusing mechanism, a precision assembly where multiple cutting tools had shaped different features of the same casting in perfect alignment. Each tool had been positioned not through measurement and adjustment, but through built-in mechanical references that automatically located the cutting edge in exactly the right position relative to the workpiece. The key was not trying to position tools accurately, it was building the accuracy into the tools themselves. Swasey's innovation centered on integrated stops built directly into each tool holder. Traditional lathes positioned tools through a complex process of measurement, calculation, and incremental adjustment that consumed hours and required extensive skill. Warner and Swasey's breakthrough eliminated this entire process by pre-machining tool holders with built-in mechanical stops that automatically positioned against the turret's headstock casting. The technical implementation required precision manufacturing that pushed their capabilities to the limit. Drill holders were machined with integral collars, ground to exact dimensions that would stop against the turret face at precisely the right depth for each operation. The collar's thickness determined how far the drill would penetrate into the workpiece, eliminating the need for depth measurement and adjustment. Boring bars were ground with precise shoulders that automatically positioned the cutting edge at the correct distance from the spindle centerline, ensuring that bored holes would be perfectly concentric with the workpiece axis. Threading tools presented the greatest challenge, requiring alignment that was both axial and radial to cut threads with proper pitch and depth. Swasey developed tool holders with reference surfaces machined parallel to the cutting edge, allowing the tool to align perfectly with the spindle axis when the reference surface contacted the turret mounting face. The threading tool's position was determined entirely by the precision of the tool holder's machining, not by the operator's skill in positioning it. The revolutionary setup process reduced tool changing to 3 simple steps that required no measurement, no adjustment, and no specialized skill. The operator inserted the pre-made tool into the appropriate turret position, taking 30 seconds to slide the tool holder into its mounting socket. Engaging the turret lock required another 15 seconds to rotate the cam lever that secured the tool holder against its reference stops. Starting machining was immediate. No test cuts, no measurements, no fine-tuning required. Total setup time had been reduced from 60 to 110 minutes to 45 seconds, representing a productivity improvement that seemed impossible to traditional manufacturers. Samuel Winton, desperate to meet Columbia Bicycle Company's exploding production demands, agreed to test the Warner and Swasey system despite industry skepticism about American manufacturing shortcuts. The first production trials in late 1886 exceeded every expectation. Each 6-station turret could complete complex bicycle hubs, shoulder turning, drilling, boring, threading, facing, and cutoff, without stopping the machine or repositioning the workpiece. The turret rotated between operations in seconds, with each tool automatically positioned for its specific cutting operation. Parts emerged from the machine complete and identical, requiring no hand fitting or individual adjustment. Columbia's production statistics told the story with brutal clarity. 500 bicycle hubs per day versus 50 per day with traditional lathes. Consistency improved dramatically, with less than 1/1000th of an inch variation between parts compared to the several thousandths typical of handset operations. Semi-skilled workers following color-coded operation sequences achieved precision that matched master machinists while working at 10 times the production rate. The secret lay in permanently dedicating each turret position to specific operations with custom tooling that eliminated every variable the traditional system introduced. Position 1 faced the hub's mounting surface to exact thickness. Position 2 drilled the center hole to precise diameter and depth. Position 3 bored the hole to final dimension with perfect concentricity. Position 4 cut threads for spoke attachment with accurate pitch and depth. Position 5 chamfered edges to remove sharp corners. Position 6 performed the cutoff operation, parting the finished hub from the raw stock. No measuring was required, no adjusting was necessary, no skill was needed beyond following the predetermined sequence that Swasey had encoded into the mechanical system itself. The operator simply loaded raw material, started the machine, and removed finished parts as the turret automatically indexed through its programmed operations. By 1900, Warner and Swasey had incorporated as a manufacturing company and placed greater emphasis on their profitable turret lathe business than on their original precision instruments. Their Carnegie Avenue factory employed over 200 workers producing turret lathes for manufacturers throughout the industrial Northeast. Each machine represented a complete manufacturing system, not just a tool, a mechanical embodiment of the production sequence that transformed raw materials into finished parts without human intervention in the precision aspects of the operation. The bicycle boom of the 1890s transformed Warner and Swasey's experimental turret system into the foundation of American mass production. What had begun as a solution to telescope manufacturing precision became the key to producing thousands of identical components for an industry that seemed to expand exponentially each month. Samuel Winton's success at Columbia Bicycle Company had generated ripple effects throughout Cleveland's manufacturing district, as competitors struggled to match production rates that seemed to defy the fundamental economics of precision machining. Traditional shops found themselves trapped in an impossible situation during the peak demand years of 1895 through 1900. Bicycle manufacturers needed not just hundreds but thousands of identical hubs, axles, pedal assemblies, and gear components to satisfy a market that had exploded from luxury novelty to mass transportation. Heinrich Zimmermann's Germania Machine Works, still operating with European-trained master machinists and traditional setup methods, could produce perhaps 50 bicycle hubs per week with their entire workforce dedicated to the task. The consistency problem proved even more devastating than the production rate limitations. Traditional shops achieved precision through individual skill and constant adjustment, which meant each setup was subtly different from the last. Parts might fall within acceptable tolerances individually, but the accumulated variations made true interchangeability impossible. A hub machined on Monday might require hand fitting to mate with an axle produced on Friday, despite both parts meeting their individual specifications. Warner and Swasey's turret system eliminated these variations by removing human variables from the precision aspects of manufacturing. Each tool position was locked into its correct location by mechanical stops rather than operator judgment. The first hub produced in a batch was dimensionally identical to the thousandth, because the machine's mechanical references ensured that every cutting operation occurred in exactly the same position relative to the workpiece. Columbia Bicycle Company's production floor in 1898 resembled nothing that European manufacturers had ever imagined. Rows of Warner and Swasey turret lathes operated simultaneously, each machine completing a different bicycle component according to its dedicated tooling configuration. Semi-skilled operators, many of them recent immigrants with no traditional machining training, followed color-coded operation cards that specified the sequence for each turret position. The hub production line demonstrated the system's revolutionary capabilities most clearly. Raw steel bar stock entered the first turret lathe, where position 1 faced the material to precise length, and position 2 drilled the center hole to exact diameter. The partly machined hub moved to a second turret lathe configured for the next series of operations. Position 3 bored the center hole to final dimension. Position 4 cut the threads for spoke attachment. Position 5 chamfered all edges, and Position 6 performed the final cutoff operation. Each hub required exactly 12 minutes of total machining time across both turret lathes compared to the 4 to 6 hours required for traditional individual setup operations. More importantly, dimensional consistency between parts measured less than 0.005 of an inch, precision that master machinists could achieve only through constant attention and frequent adjustment of their hand-set tools. The economic impact extended far beyond production rates. Columbia's cost accounting revealed that labor expense per hub had dropped 70% compared to traditional manufacturing methods. Semi-skilled operators earned substantially less than master machinists, and each operator could tend multiple turret lathes simultaneously, since the machines required no constant adjustment or monitoring during the cutting cycles. Training time collapsed from the years required to develop traditional machining skills to weeks of instruction in following predetermined sequences. New employees learned to identify the correct turret position for each operation, ensure proper workpiece loading, and recognize when cutting tools required replacement due to wear, The precision aspects of the operation, tool positioning, feed rates, cutting speeds, were built into the mechanical system and required no operator judgment. Cleveland's emerging automotive industry provided the ultimate test of the turret system's capabilities. Companies like Alexander Winton's Motorcar Works and the White Sewing Machine Company's automotive division demanded precision components in quantities that made bicycle production seem modest. Transmission gears, drive shafts, and engine components required tolerances measured in fractions of thousandths, while being produced in runs of thousands of identical parts. Winton's automotive transmission project in 1902 pushed the Warner and Swasey system to new levels of sophistication. Each transmission required 47 different precision components, many requiring 5 or 6 machining operations to complete. Traditional manufacturing would have required a master machinist to set up tools individually for each operation, consuming weeks to produce a single complete transmission. The turret solution involved dedicating specific machines to component families and configuring multiple turret positions for complete part production. A single turret lathe produced transmission input shafts from raw material to finished components in 18 minutes, performing turning, drilling, keyway cutting, threading, and final facing operations without operator intervention in the precision aspects. Another turret lathe was configured specifically for gear blanks, while a third handled the various small components that required threading, boring, and facing operations. By 1905, Warner and Swasey employed over 1,000 workers in their expanded Carnegie Avenue factory complex. The original modest brick building had been demolished and replaced with Arnold Bruner's massive 5-story structure containing 220,000 square feet of manufacturing space. Their turret lathes had spread throughout America's industrial centers as manufacturers discovered that precision components could be produced by semi-skilled workers at rates that made American products competitive with European imports for the first time. European competitors initially dismissed the American approach as crude mass production, unsuitable for precision work, but visiting British engineers in 1904 returned to London with disturbing reports. American semi-skilled operators were producing transmission gears, bicycle components, and automotive parts with dimensional consistency that European master craftsmen could not match, while working at production rates that seemed to violate the fundamental relationship between speed and precision. The transformation extended beyond mere manufacturing efficiency. Warner and Swasey had democratized precision manufacturing, proving that superior mechanical systems could replace inherited skills and traditional apprenticeships. American industrial capacity was no longer limited by the availability of European-trained craftsmen or the time required to develop traditional machining expertise through decades of guided practice. Success bred overconfidence in the gleaming corridors of Warner and Swasey's new Carnegie Avenue headquarters during the prosperous summer of 1907. The company had demolished their original modest workshop in 1904, replacing it with Arnold Bruner's architectural masterpiece, a massive 5-story brick monument to American manufacturing supremacy that stretched 220,000 square feet along Cleveland's Industrial Boulevard. Orders flooded their sales department from automotive manufacturers throughout the industrial Northeast, each contract more ambitious than the last as Detroit's emerging motor companies demanded precision components in unprecedented quantities. The crisis that would nearly destroy the company arrived disguised as their greatest opportunity. Marcus Thompson, Cadillac Motor Company's chief engineer, visited Cleveland in September with specifications that pushed beyond anything Warner and Swasey had previously attempted. Cadillac's new Model 30 required transmission gears cut to tolerances of 5/10,000ths of an inch across multiple machining operations, precision that approached the limits of measurement technology itself. Thompson's engineering notebooks contained detailed drawings of gear teeth that required not just accurate dimensions, but perfect surface finish and absolute concentricity between multiple diameters. Each transmission gear underwent 6 separate machining operations: rough turning to approximate diameter, finish turning to final dimension, gear tooth cutting, keyway machining, hub boring, and final inspection. Traditional European manufacturers achieved such precision through constant monitoring and adjustment, by master machinists who could detect dimensional drift before it exceeded tolerance limits. Warner and Swasey's standard preset tooling system had revolutionized manufacturing by eliminating setup time, but it had never been tested against specifications this demanding over extended production runs. Swasey confidently accepted the contract for 50,000 transmission gears, believing that their mechanical positioning systems would maintain precision automatically without the constant human intervention that European methods required. The initial production trials in November 1907 appeared successful. Warner and Swasey's specially configured turret lathes produced the first 1,000 gears within Cadillac's specifications, with dimensional measurements consistently falling within the required 5/10,000ths tolerance band. Thomson approved the samples and authorized full production, expecting delivery of the complete order by the following spring. The catastrophe unfolded gradually over the winter months as production continued around the clock to meet Cadillac's aggressive delivery schedule. Warner and Swasey's production floor hummed with mechanical precision as their turret lathes cycled through the complex gear manufacturing sequence. Operators followed their established procedures, loading raw steel blanks and removing finished gears according to the color-coded instruction cards that had proven successful for thousands of previous components. By March 1908, Warner and Swasey had produced nearly 10,000 transmission gears when Thomson's quality inspector discovered the dimensional drift that would destroy the entire contract. Parts that had started within specification were gradually moving out of tolerance as subtle process variables accumulated over extended production runs. Tool wear, despite regular replacement schedules, caused cutting edges to change geometry slightly with each part produced. Thermal expansion from continuous operation shifted mechanical references by amounts measured in 10,000ths of an inch. Material variations in the steel stock introduced inconsistencies that preset tooling could not compensate for during processing. The final measurement reports revealed the devastating scope of the problem. Gears produced during the first weeks of the contract measured within 4/10,000ths of nominal dimension. Parts from January production had drifted to 6/10,000ths, still within tolerance but approaching the limits. By March, dimensional measurements exceeded 8/10,000ths, placing every gear outside Cadillac's specifications, despite following identical manufacturing procedures. Thomson's rejection of the entire 10,000-piece batch sent shockwaves throughout the automotive industry. Cadillac had built its reputation on precision and reliability, standards that could not accommodate components with dimensional variations exceeding specified limits. The rejected gears represented months of production time and material costs that Warner and Swasey could not recover, while the contract cancellation eliminated expected revenue that the company had counted on to finance their expanded operations. The technical failure exposed a fundamental limitation in the preset tooling concept that Warner and Swasey had never encountered during shorter production runs. Eliminating setup time had solved the immediate problem of tool positioning, but it could not address process variables that accumulated over thousands of parts. European manufacturers, with their constant monitoring and adjustment protocols, maintained better long-term precision because master machinists continuously compensated for tool wear, thermal drift, and material variations throughout extended production cycles. Industry publications seized on the failure as proof that American manufacturing shortcuts were inherently flawed. The British trade journal Engineering proclaimed that American industrial methods, while suitable for crude mass production, cannot achieve the sustained precision that European craftsmanship traditions have perfected over centuries. German manufacturers, who had watched Warner and Swasey's success with growing concern, used the Cadillac contract failure to reassure their customers that traditional methods remained superior for critical applications. The financial consequences proved nearly fatal to Warner and Swasey's operations. Stock prices plummeted as investors lost confidence in the company's core technology. Several major contracts were canceled as automotive manufacturers questioned whether preset tooling could meet their precision requirements. The massive Carnegie Avenue factory, built to accommodate expanding production, became a monument to overreach as orders disappeared and workers faced layoffs. Warner spent sleepless nights in his office, reviewing production data and searching for solutions to process variables that their mechanical systems could not address. The company that had revolutionized American manufacturing through superior mechanical design seemed destined to become another casualty of industrial overconfidence, proof that European skeptics had been correct about the limitations of American shortcuts. The crisis deepened when additional automotive contracts were canceled throughout the spring of 1908. Companies that had previously embraced Warner and Swasey's turret systems began questioning whether preset tooling was suitable for their most critical components. The revolution that had democratized precision manufacturing appeared to have reached its limits against the unforgiving demands of sustained accuracy over extended production runs. Swasey retreated to his design workshop, surrounded by failed gear samples and measurement reports that documented the systematic drift his mechanical systems could not prevent. The breakthrough that had eliminated setup time now seemed inadequate against process variables that required human judgment and constant adjustment, exactly the elements that their revolution had been designed to eliminate. From the brink of bankruptcy, in the autumn of 1908, Ambrose Swasey engineered what would become Warner and Swasey's masterpiece, the self-compensating turret system that transformed their near-fatal failure into the foundation of modern mass production. The solution emerged not from abandoning their revolutionary preset tooling concept, but from evolving it to address the process variables that had destroyed the Cadillac contract. Swasey's breakthrough combined mechanical genius with manufacturing precision that exceeded anything the company had previously attempted. Instead of single-point tool positioning that could not adapt to changing conditions, the new design featured adjustable stop collars on each tool holder, calibrated to compensate for predictable wear patterns that accumulated over extended production runs. Each collar incorporated precision ground surfaces that could be adjusted in increments of 2/10,000ths of an inch, allowing operators to maintain dimensional accuracy as cutting tools gradually wore during processing. The spring-loaded positioning systems represented the most sophisticated mechanical innovation in the entire design. Traditional rigid stops had locked tools in fixed positions that could not accommodate thermal expansion or material variations. Swasey's spring-loaded mechanism maintained constant contact pressure against reference surfaces while allowing microscopic adjustments that compensated for temperature changes and material inconsistencies. The spring tension was carefully calibrated to provide consistent positioning force without introducing vibration or instability during cutting operations. Most revolutionary were the modular tool cartridges that could be preset offline and swapped during production without stopping the manufacturing process. Each cartridge contained a complete tool assembly, cutting tool, holder, reference stops, and adjustment mechanism configured for specific operations on particular components. When Marcus Thompson returned to Cleveland in February 1909 with specifications for Cadillac's new transmission design, Warner and Swasey could guarantee dimensional consistency by providing pre-configured tool cartridges that had been tested and calibrated before installation. The tool library concept transformed precision manufacturing from a craft requiring individual skill to a systematic process based on mechanical precision. Pre-machined tool assemblies for specific parts were stored ready to use in climate-controlled cabinets, each cartridge labeled with the component it would produce and the dimensional tolerances it would maintain. When Cadillac ordered transmission gears, operators simply loaded the Cadillac transmission turret configuration, 6 tools, pre-positioned, pre-tested, and guaranteed to maintain 5/10,000ths tolerance through 50,000 parts without dimensional drift. The results exceeded every expectation that the automotive industry had established for American manufacturing precision. Setup time was reduced to 3 minutes for loading pre-configured tool cartridges, compared to the 60 to 110 minutes required for traditional tool positioning. More critically, precision maintenance improved to 3/10,000ths throughout 50,000-part production runs, surpassing the consistency that European master machinists could achieve through constant monitoring and adjustment. Operator skill requirements were reduced to following color-coded sequences that eliminated judgment calls and potential errors. Each tool cartridge was marked with distinctive colors that corresponded to specific operations and turret positions. Operators needed only to match colors and follow predetermined sequences, no measurement, no adjustment, no specialized knowledge of cutting speeds or feed rates. The precision aspects of manufacturing were built into the mechanical systems and required no human intervention. Production rates that had seemed impossible under traditional methods became routine achievements. Warner and Swasey's new self-compensating turrets could produce 2,000 precision transmission gears per day while maintaining dimensional consistency that European manufacturers achieved only in small batches through intensive skilled labor. The economic advantages were staggering. Labor costs per part dropped below levels that European competitors could match even with their lowest-paid apprentices. Cadillac's 1909 order for 100,000 transmission gears provided the ultimate test of the evolved system. Thompson's specifications remained demanding, 5 10,000ths tolerance across 6 machining operations, but Warner and Swasey's tool cartridge approach eliminated every variable that had caused the previous contract failure. Each cartridge was calibrated offline using precision measuring equipment and test materials, ensuring dimensional accuracy before production began. The manufacturing process resembled a carefully choreographed mechanical ballet. Pre-configured tool cartridges moved between turret lathes according to production schedules that maximized equipment utilization while maintaining quality standards. Operators changed cartridges in 3-minute intervals, transforming their machines from transmission gear production to bicycle hub manufacturing to automotive axle processing with mechanical precision that eliminated setup errors. Quality control data from the Cadillac contract documented the systematic nature of Warner and Swasey's achievement. Dimensional measurements remained within 3 10,000ths of nominal specifications throughout the entire 100,000-piece production run. Surface finish consistency exceeded specifications by substantial margins. Concentricity between multiple diameters measured better than European hand-fitted components, despite being produced at rates that traditional methods could never approach. The vindication was complete when Cadillac's final inspection reports showed rejection rates below 1%, better than any supplier in their network, including prestigious European firms that had dominated precision manufacturing for centuries. American semi-skilled operators using Warner and Swasey's self-compensating turret systems had achieved precision and consistency that European master craftsmen could not match through traditional methods. By 1928, Warner and Swasey had become the world's leading manufacturer of turret lathes, with their self-compensating systems installed in factories throughout America and Europe. Their preset tooling concept had evolved into the foundation of modern mass production, enabling the automotive revolution that transformed American society and established industrial dominance that would persist through the 20th century. European manufacturers, once dismissive of American shortcuts, began licensing Warner and Swasey designs and sending engineers to Cleveland to study manufacturing methods they had initially rejected as crude and unsuitable for precision work. The revolution that had begun with eliminating setup time had created something greater: the democratization of precision manufacturing that made complex components accessible to semi-skilled workers through superior mechanical systems. The transformation was complete. What had started as a solution to tool changeover problems had revolutionized the relationship between skill and precision in manufacturing. Master craftsmen were no longer required for precision work when mechanical systems could encode their knowledge and exceed their capabilities through systematic innovation that eliminated human variables from the critical aspects of production.